So students, today we discuss about Rydberg constant and wave number. আজি আমি Rydberg constant and wave number topic to discuss. Okay. So last class we get the expression of total energy of electron in hydrogen atom. That is the total energy. This total energy of electron is En equal to in hydrogen atom En equal to in terms of K minus of 2 pi square K square e to the power 4 m divided by n square h square. This is in terms of K, that means Coulomb's constant. Again, in terms of permittivity, we get minus of m. If we apply K equal to 1 by 4 pi epsilon naught, then we get m e to the power 4 divided by 8 epsilon naught square n square h square. So this is the expression of energy in ground state, that means n at orbit. Already we know this energy, that means total energy of the electron, that is negative in an orbit. Total energy is negative. So why total energy is negative? Because the electrostatic force in between electron and nucleus always attractive. Electrostatic force in between electron and nucleus always attractive. Therefore, the total energy of an atom becomes negative. Okay? So there is a question why total energy becomes negative. Because the total energy in between, that means the electrostatic force in between nucleus and electron always attractive. Therefore, the total energy, that means attractive. Therefore, the electrons are bound with the nucleus. So, the total energy becomes negative. Okay. So, this is total energy. So, according to Bohr's postulate, we know if an electron is jumped from higher energy level to lower energy level, so then they can radiate energy. That means they can release energy. Okay. So, if you apply Bohr's postulate for electron jump from higher energy level to lower energy level, then we get if an electron is jumped from higher energy level to lower energy level, then we get EI minus EF equal to H nu, EI minus EF equal to H nu, then H nu equal to first EI. I mean, yet if we apply, here all are same, m, e, this part is same, but n is different. Yet, but n is different. So, this n becomes ni. So, m e to the power 4, 8 epsilon naught square, a square into ni square, minus, again, this is negative sign of the formula, then next, negative sign of the expression of energy. It will be minus m e to the power 4, 8 epsilon naught square a square and f square. Okay, so in these equations already we get m e to the power 4 h nu equal to m e to the power 4 divided by 8 epsilon naught square a square is constant, then 1 by, it will be minus plus n f square minus 1 by n I square. Okay. So this nu means frequency. This is H, nu means C by lambda. H C by lambda equal to m e to the power 4 divided by 8 epsilon naught square h square 1 by n f square minus 1 by n I square. Okay. So this 1 by lambda equal to m e to the power 4 divided by 8 epsilon naught square c h cube a square H যদি তলে যায় CH cube equal to 1 by n f square minus 1 by n I square. M e to the power 4 8 epsilon naught square CH cube into 1 by nf square minus 1 by ni square. So this value is known as Rydberg constant, that is R. Okay, so R into 1 by n f square minus 1 by n I square. Okay, so this is the expression. This is the expression of wave number. This is the expression of wave number. Where expression of wave number where this R is equal to, this R is known as Rydberg constant. Okay, so this R is equal to m e to the power 4 8 epsilon naught square CH cube is equal to 1.097 into 10 to the power 7 meter inverse. So this is known as Rydberg constant. R is equal to m e to the power 4 8 epsilon naught square CH cube equal to 1.097 into 10 to the power 7 meter inverse is known as Rydberg constant. So this is the expression. This is the expression of Rydberg constant. It is the expression of Rydberg constant. ঠিক আছে? So next, wave number. So what is wave number? Wave number is reciprocal of wave number. Reciprocal of wavelength 1 by lambda. So 1 by lambda is the reciprocal of wavelength and it is known as wave number. So this is the expression of wave number. So from this already we get this R equal to m e to the power 4 8 epsilon naught square CH cube equal to 1.097 into 10 to the power 7 meter inverse is known as Rydberg constant. Rydberg constant and 1 by lambda equal to nu bar is equal to wave number. So this is the expression of this. Okay, so here this part is complete. Expression of Rydberg constant and wave number. Okay, so next we discuss about the spectral series. That means spectra. That means we discuss about the hydrogen spectra, which is Lyman, Balmer, Paget and Brackett. Okay, there are 5 series, spectral series. We get Lyman series, Balmer series, Paget and Brackett series. Okay, so now we discuss this spectral series of hydrogen atom. So now first of all discuss about spectra. So spectra means we know in an atom emitter can be classified into 3 types. That means solid, liquid and gas. Okay, so spectra means this solid, liquid and gas emit the electromagnetic radiations due to the solid, liquid and gas. Okay, this solid, liquid and gas emit electromagnetic radiations at all temperature due to oscillations and interactions in between atoms and molecules. Which are obtained lying side by side in band of colors. So this is known as spectra. So spectra means, what is spectra? Spectra means solid, liquid and gas emits electromagnetic radiations at all temperature due to oscillations and interactions in between atoms and molecules, which are obtains in band of colors and lying side by side is known as spectra. Okay, so this spectra is mainly classified into two types. First one is emission spectra. First one is emission spectra, that means line emission spectra. Second one is absorption spectra. Line absorption spectra. So what is emission spectra and what is absorption spectra? So emission spectra means when electric current, this is emission spectra, when electric current is passing through atomic gas or vapor, then some bright lines are obtained on dark background. Some bright lines are obtained on dark background. So this spectra is known as line emission spectra. That means when electric current is passing through atomic gas or vapor, then some emissions takes place in line on dark background. So these bright lines obtained on dark background is known as line emission spectra. Okay? Similarly, if white light having wavelength 700 nanometer to 400 nanometer, visible light, that means when white light is passing through atomic gas or vapor, then some emissions, then some lines are absorbed. That means some spectra are obtained which are absorbed. So that spectrum is known as absorption spectra, line absorption spectra. That means we get two types of spectra. First one is emission spectra, which is obtained on dark background when electric current is passing through atomic gas or vapor. That is known as line emission spectrum. Next, when the white light is passing through atomic gas or vapor, then some spectra are absorbed. That means some lines are absorbed. Therefore, some dark lines are obtained. So that spectra is known as absorption spectra. That is line absorption spectra. So in case of spectra, line absorptions or line emission spectra, we get some spectral series. That means we get some group of colors. Which are obtained due to different wavelength of all the colors. Okay, so that series obtained in the group of colors are known as spectral series. So actually, what is spectral series? So spectral series means the spectrum of element has wavelength. The spectrum of element has wavelength, so definite regularities which can be classified into groups. They are known as spectral series. Okay, so what is spectral series? The spectrum of all elements. Has wavelength. So definite regularities. In a group. Regularities in a group. That means they are classified in a group. Okay, so that is known as spectral series. Okay, so we know in case of hydrogen there are 5 spectral series. That is Lyman series, Balmer series, Paschen and Beckett series. Okay, so now we discuss spectral series of hydrogen atom. Okay, so in spectral series of hydrogen atom, here we consider 6 circle. So in which we get spectra. First one is Lyman series. Lyman series means when transitions occur from higher energy level to n equal to 1. That means higher energy level from 2, 3, 4, 5, 6 to 1. That's are known as Lyman series, like this. Like this. These transitions occur from higher energy level 2 to 1. Next 3 to 1. Next 4 to 1. Next 5 to 1. Next 6 to 1. This is Lyman series. This is Lyman series. Transitions occur from higher energy level. That means what is Lyman series? The transitions occur from higher energy level. That means Ni equal to 2, 3, 4 infinity to Nf equal to 1. Transitions occur from higher energy level 2, 3, 4 infinity to Nf equal to 1 are known as Lyman series. Okay, so in that case, in case of Lyman series, we get the wave number 1 by lambda equal to R. For first transitions, we get 1 by lambda equal to R, equal to 1 by 1 square minus 1 by Ni square. Okay, for Lyman series, we get 1 by lambda equal to R, to 1 by 1 square minus 1 by Ni square. For first transition, Ni equal to 2. For second transition, Ni equal to 3. For third transition, Ni equal to 4, like this. So in that case, the ground state is 1 and first excited state is 2. So we know already last class we get the energy of first state, that is minus 13.6 electron volt. In second state, minus 3.4. Third state, minus 1.5. Fourth state, 0.85. Fifth state, 0.54. Sixth state, 0.38, minus 0.38. And seventh state, minus 0.28 electron volt. So these are the values of energy in different states. That means first ground state, then when we go from lower energy level to higher energy level. Okay, so this is for Lyman series. So in Lyman series, we get ultraviolet radiations takes place. That means here UV radiations takes place. UV radiations takes place in Lyman series. Okay, so next we consider Balmer series, in which the transitions occur from higher energy level to higher energy level 3, 4, 5 to n equal to 2. That means this is second state. That means transitions will be come to this state 2. From first transition is starting from 3 to 2, like this. Next 4 to 2. Next 5 to 2. Next 6 to 2. So this is Balmer. So in that case, what happened in Balmer series? That in Lyman series, here we get in Balmer series. Next, in Balmer series, Ni equal to 3, 4 infinity to equal to 2. So here this is 2 square. Others are same, and here we get visible light. Visible light takes place in Balmer series. Okay, so that means what is Balmer series? The transitions occur from higher energy level 3, 4, 5 infinity to Nf equal to 2 are known as Balmer series. Okay, so next one is Paschen series. So in Paschen series, ground state becomes 3. That means transitions occur from higher energy level 4, 5, 6 infinity to transitions occur to 4. Okay, so this is 1, 2, 3. Next is 3. Transitions occur from higher energy level to 3. That means first transition is starting from 4. This is 4th state, 4 to 3. This is percent. Okay, so in case of percent series, what happened? In case of percent series, this starting from 4, 5, 6 to Ni equal to 3, then it becomes 3 square. So here we get infrared radiation. Infrared radiation takes place. For first tension of percent series, we get for first tension Ni equal to 4 and Nf equal to 3. For first tension, this will be 4 and it will be 3. Okay. So first let's say the longest wavelength of each spectral series is the first tension. That means each spectral series, its longest wavelength is first transition. That means first transition of each spectral series has longest wavelength and last transition is known as shortest wavelength. Okay, so here in case of Lyman series, so first transition is occur from in case of Lyman. Okay, so in case of Lyman, first transition is occur from 2 to 1. First transition, which is longest wavelength, that is 1215 angstrom. Points to be marked, points to be remembered. The wavelength of first transition of Lyman series, which is longest wavelength, that is 1215 angstrom. 1215 angstrom. Okay. So next, second transition. In second transitions, last transitions, which is shortest wavelength of Lyman series is 911 angstrom. That means Lyman series is occur in between 911 to 1215 angstrom. That is Lyman series. Balmer series, first transition is come from 3 to 2. So this longest wavelength of Balmer series is first transition. That means 3 to 2. 3 to 2. That is 6563 angstrom. This is first transition. Okay. So like this. So this is percent series. So here infrared radiation takes place. Now percent. Now is bracket series. 3. This is bracket. Bracket series. Here ground state becomes 4. That means these transitions occur from 5 to 4. Next, like this. This is bracket. Okay, so here Ni equal to 5, 6, 7 infinity to Nf equal to what? This is 4. So 1 by lambda R 1 by 4 square minus 1 by N I square. That means for first tension N I equal to 5, for second tension N I equal to 6. So here also infrared radiation takes place. Here also infrared radiation takes place. So you face questions, what type of transitions takes place when radiations occur from suppose 6 to 3. 6 to 3. 3 means Lyman, Balmer, percent. So percent series. So in percent series we get infrared radiation. Suppose 6 to 2. 2 means Balmer series. So in that case the light will be visible light. Okay. So next last one is bracket series. Fan. So in that case the ground state is 5. So here this is fan series. This is transitions occur from 6 7s like this to N equal to 5. This is P fan. That is fan series. Okay. this is 6, 7, infinity to this will be 5. Okay, so here also infrared radiations takes place in P-fan. That means in between Paschen bracket and P-fan, in this we get infrared radiations in this, and here we get visible in Balmer series, and in Lyman series we get ultraviolet radiations. Okay, so this is the spectral series of hydrogen atom. So from this we get a band of wavelength. That means we get a range of wavelength. Okay, that is C. So students, now see, we get different series and different range of wavelength. Okay, so first one is spectral series. Next, longest wavelength. That means first transition of each spectral series has longest wavelength, and last transition of each spectral series has shortest wavelength. So first is Lyman series. So in that case, Lyman series is first transition is occur from 2 to 1 state. That means initial state is 2 and final state is 1. Therefore, is maximum value. That means wavelength becomes maximum. That is 1 to 1.5 angstrom. Next, shortest wavelength is coming from infinity to 1. Infinity to 1. So this shortest wavelength becomes 911. So Lyman series is range of Lyman series is 911 to 1 to 1.5 angstrom. Okay, that means we can easily understand this 911. That means 910 to. That means we can easily understand 900 to suppose 1200. We can easily remember this 900 to 1200. Okay. So next is Balmer series. So its first transition is starting from 3 to 2. Ground state is, in case of Balmer series, ground state is 2. So first transitions occur from 3 to 2. So wavelength is first transition wavelength 6559 angstrom. And maximum, then this is maximum wavelength, and minimum is which is coming from higher energy level. That means infinity to second energy state, which is minimum, that is 3644. So this range is, that means 6500 to 3600. We can easily understand. That means 3600 to 6500. Okay. Next is Paschen series, which is similar, is 4 to 3. Ground state is 3, higher tension is 4. That means 4 to 3. That means lambda is maximum. First tension of wavelength is 18,741, and this last tension of wavelength is 8,199. So it can be easily remembered. That means 8,200 to 18,000. Okay, 8,200 to 18,000. Okay. So next, bracket series, which is maximum wavelength 40,000. Bracket series, first wavelength, first tension maximum wavelength is 40,000 and last tension is 14,000. That means 14,000 to 40,000. Okay, in that case. So in which alpha radiations takes place. From Paschen to fan series, Paschen to fan series, we get infrared radiation. Paschen opera, Fandole ami ki paisu, infrared radiation paisu. Next, bracket series dekhile. Fan series palo, that is maximum wavelength 74,000 and minimum is 22,000. Okay, so this is the range of wavelength. Okay, and range of wavelength of different colors, different spectral series. Okay, so already spectral series, and we discussed about the energy level diagram. Okay, which is also similar energy level diagram. Already last class we get this energy level. Okay, so next we discuss about Bohr's dropping and excitation energy and ionization energy. Okay, so thank you.